All right, welcome everybody. We'll give it just a few minutes here to allow all the attendees to jump in, and we're coming right off of lunch right here, so I understand priorities.
Food always comes first.
It does, it does. It's one of the best parts about being a member of Design Point. We love our food here.
There's no such thing as too much.
Amen. All right, looks like our list is growing here, so that's good. See a couple familiar names here. Welcome, guys. Some new people as well. All right, I think we'll go ahead and get started right here. Go through our introduction as some other people join up right here. Looks like the list is still growing slowly, so that's awesome. You guys picked the best presentation to join today, so thank you for that. So we're here to talk about simulation and how that can influence some of our designs, specifically a design you might have seen throughout the day here. So I'd like to start off by introducing us here. My name is Ryan Borger. I have my colleague here, Julio Colles, and we are known as the Sim Guys. We're the Sim specialist here for Design Point, and that's pretty much what we're obsessed with, which is awesome. So we're going to share that obsession with you guys here today and talk about 3 different sim tools, actually. Some of them maybe you've seen before, some of them maybe you have, but hopefully it will influence you to take a look at those tools as an opportunity to work with our designs on a daily basis. And the design we're going to be working with today is the quadcopter. So hopefully you saw previous presentations earlier. I know Andres and Abby did a great presentation on how we did the project management for this quadcopter through the 3D platform. And Breland and Dan Lawrence, they did a great presentation on the actual manufacturing of this. And hopefully you knew, if you didn't know, this was 3D printed, and they have some cool pictures of this live and printed. So without further ado, let's go ahead and jump into it and see what kind of trouble we can get into. So we were tasked with taking a look at the frame of this quadcopter. It's what we're manufacturing. There are some purchase parts here, like the motors, the propellers, some of the internal electronics, things like that. We've purchased all that stuff to put it all together. But Julio and I were tasked with testing this frame in worst case scenarios to make sure that the design is set up to work with what we need. And we split this project up into 2 different parts. I focused on the FEA side of the frame, and Julio, you're going to see a little bit later on this presentation here, he focused on drop testing this to see what happens if it falls out of the sky and breaks. So for my part here, what we wanted to take a look at was, with the blades that we chose and the motors that we picked, we wanted to see at full throttle, if we were holding this thing down on the ground, if it was stuck somewhere, what sort of thrust forces are we looking at based on those purchase parts? And with that thrust force, how does that translate into the frame? And do we actually design a good enough frame to hold that power, and see if we need to make any changes from there? So we're going to take a look at those through using 2 different tools. We're going to look at flow simulation to gather our thrust forces, and then we're going to look at FEA simulation to take a look at the actual stress analysis throughout the part. So what I'd like to do here is jump into SOLIDWORKS and show you the model that we're working with. I got this from Dan Lawrence, who was working on this design. So he gave me all these parts and pieces right here already put together. And I'm going to start off with the flow simulation. So for those of you who are not familiar with flow simulation, or any of the sim packages for that matter, they are a function of SOLIDWORKS. It's an add-in, depending on your license type that you may acquire or may have. And it's all built right in within your SOLIDWORKS window, which makes it easy to work with, a familiar environment, if you will. So what I'm looking at right now is the overall model over here in my graphics area. But if we take a look over at the design tree, we can see it might look a little bit different if you're not familiar with flow simulation. And what I'm looking at now is what's known as the simulation design tree. And we have different studies and so on and so forth. So what I did for this first study is I wanted to take a look at these propeller blades, which again, we purchased these, we didn't design them. Now, we could certainly design them and try to tweak it if we wanted to, but we were kind of on a time crunch, as everybody always is, right? So it's a very realistic situation. So based on these designs, I want to see what sort of power they're putting out. The motors that we purchased, they spin at 14,000 RPM each. So what I did is I set up what's known as a rotating region. And if I take a look in the model right here, you can see this little flag that just popped up when I clicked on this thing over here under rotating regions called CW1. This is basically me telling the software there's going to be fluid, in this case air, rotating around the blade. And that might sound a little odd, right? Rotating around the blade, why not rotate the blade? Well, computationally speaking, it's very difficult to rotate the blade. Not impossible, but from the computational standpoint, it will take a lot of power and a lot of time to solve something that's, well, relatively simple. So what we're going to do is instead we're going to tell the blade to hold still and allow the air to move around it. And it's the same thing. It's imagine if you were to hold, say, a nut in your hand and thread a bolt one direction versus another direction, the threads go the same way regardless. So that's kind of what we're looking at with the rotating region here. And I have 4 of them set up just so we can see all 4 of them. Even though they're all going to put out the same amount of power, I could have saved some computational time by doing only one, but I was a little obsessed with it. So we did all 4 of them. And to make it really interesting with it too, based on Breland, our expert on these quadcopters, his advice was that when we build these things, we want to make sure that our rotations on each of these motors are opposing each other on a diagonal. We don't want all of these things spinning clockwise, otherwise the entire thing will spin on us and that won't be easy to control. So I have 2 rotating regions, one right here and one right here that's spinning clockwise, and then 2 that are spinning counterclockwise, and that kind of balances everything out. And I wanted to take that into consideration as well too with some of the forces. So that's another reason why we want to do all 4 of them right here. Now, the way flow simulation works is we have to use what's called a goal in order to pull data that actually matters to us and to help kind of solve this more accurately. There's tons and tons of different variables depending on what you're trying to look for that can help quantify the solving of a study. And an engineering goal, which is what we're looking at over here, this little flag, is just another way to bring that out and tell the study that this is the specific piece of data that I care about, and this is what I want to converge. And in this case, I chose to create 2 goals. One goal, this first one here, we're just called force 1. This is for the thrust of all 4 propellers working as one. And the second one right here is I just wanted to isolate it a little bit. I just care about, say, the force in the Z direction. In this case, if we look at my triad down here, the Z direction is relative up and down to our model. I just want to see what that force is in this case and see what's happening. All right, so study time. This one did not take too terribly long to run. It took about 10 minutes to run this study at a pretty refined mesh right here. So I did already set this up for us so we don't have to sit here and watch a little green bar go across the screen, as fun as that is to watch. But let's take a look at some of the results here. The first thing I want to do is I want to make sure I set this up correctly. And that is going to be an easy way to tell is through my flow trajectories. So if I show my flow trajectory plots right here, we can take a look at these arrows that are representing the direction of fluid flow, in this case, again, air. And you can see how they're pointing down. So that's one really good sign, right? To have the force going in the correct direction. And you can even see, it looks like they're rotating a little bit right there. That's, again, indicating that we have a rotating region around these blades themselves. And who doesn't like an animation? If we want to get a little fancy with it, I can go ahead and play that, and we can really see how that air is rotating around those fan blades right there. So great information. We have the study set up correctly. It's working as I would expect it to at this point, which means I can trust the data that I'm about to pull out of it. So speaking of the data, let me just hide this flow trajectory right here. We're going to move down to our goal plots here. So these are tied directly to the goals that we use to converge this study. And this is how I'm going to pull the information out that I need to run in our FEA study. So I don't necessarily care about that flow anymore. Now I care about what force is that flow applying to the model. And if I take a look at one of these goal plots, again, one of them is for the overall force, one is for each individual one. I'm going to look at just the individual ones for right now. And we can see that it looks like each one of these motors with the blades spinning at 14,000 RPM is pulling out close to a half a pound of thrust. And again, I did confirm this with Breland, and this turns out to be pretty average, pretty standard for this type of blade design and this type of motor. So again, a good validation right here that the software is doing what we would expect it to do at this point, and our study is set up correctly. So this is looking good. All right, so with that information, I can now call my work in flow simulation done at this point, because flow simulation, it's only for fluids, right? It's just telling me how things are moving in and around models with respect to geometry that we have there. It doesn't allow me to do any kind of stress analysis whatsoever. So now we're going to tie into another SOLIDWORKS tool, which is going to be just what's known as simulation, FEA simulation, which just like flow, is another add-in to the software. So I'm still within SolidWorks at this point, working with everything all together. And that's important for whenever we have to do design changes or make some tweaks or add or remove things, we can have it basically automatically update our studies as we need them to, depending on how we want to take that. Now you notice when I jumped into my FEA study, some things disappeared. It's gotten more simple at this point. And that's because when it comes to simulation, if you want to get any kind of good takeaways, any tips I can give you with simulation, if you're running these things, is keep it as simple as possible. Take out the things that you don't need and the things that you don't care about and try to represent them differently. For instance, I'm trying to run an FEA on the frame, and I do care about the battery box in this case. We'll talk about a little bit more of that battery box, why it's important when Julio does his drop test in a little bit here. But since I only care about the frame, there's no need to figure out what sort of stresses are happening within the motor and within the propellers based on the tasks that were given to us. We might change that mind a little bit later on down the road, but for now, we only need the frame. So I have all those extra parts and pieces pulled out, which will significantly increase the performance of our studies here. All right, now taking a look at our simulation design tree for FEA, it's pretty much set up the same way as any other design tree we've worked with here. We just have a bunch of information all put together to set up the study. And I do want to turn your attention specifically to the materials, because materials make or break your sim studies, regardless of whatever you're doing. You can have the best setup study whatsoever, but if you don't have the correct materials, you're not working with the correct data here. Now, we are 3D printing this frame out of Onyx, which is from our Mark II or our Mark Forge line of printers. And Onyx is essentially nylon with crushed up carbon fiber. Now, in order to get that material into SolidWorks, you can see I have a material here called Onyx. This is one that I created custom. And you're probably wondering, well, how did you create a custom material? Well, all I did was I went to the Mark Forge website and they have all the material data right here for me that I could just copy and paste from their website into SolidWorks to create my own material. Now we're working with, if you're familiar with the Mark Forge printer line, we're working with no fiber in these whatsoever, but we do have material data for fibers if we wanted to, depending on how we're taking this. So we're gonna kind of go the worst case scenario. If this thing can be strong enough without fiber, if we ever do decide to put fiber in it for whatever reason, it's probably gonna be better at this point. So we're just keeping it simple for right now. So we can see that material is applied to our frame and our battery box right here. And there's a bunch of other things suppressed at this moment. Those are all the extra parts and pieces that we don't need, like the motor and the propellers and so on and so forth. All right, so pretty simple. Now, as far as this study is concerned, we have to have what's known as a fixture. And a fixture is going to basically tell this thing how it's bounded. We do have to have some kind of a holding power on this thing in order to run it within this type of simulation study. And what we're going to simulate here, if I rotate the model around a little bit, you can see I have this fixture here that's highlighting this blue face on the bottom of the battery box. What I'm basically trying to simulate is this battery box is, say, glued to the ground, or you're holding it in your hand, and it's not going to move via that face whatsoever. No matter how hard we push the limits here, it's not going to move, and that's going to give us our worst case scenario here. Moving on down here, we can see we have a force applied here. So I have a thrust load that I added to these faces. Let me just highlight that again so you can see. Now I'm just simplifying this again for the purpose of demonstration here. We could make these faces maybe a little bit more accurate for where the force is applied, but this is actually giving us some pretty good results. So we'll keep it, again, as simple as possible. And it has that nearly ½ pound of force applied to each one of those faces individually. It's not a total, it's a ½ pound at each individual face right here. So that's looking pretty good. Now, as far as running these studies is concerned, besides your materials, the next thing that can make or break it here is going to be your mesh. If your mesh isn't set up correctly, you're not going to get really good, accurate results. Another tip I'll give you right here, if you're not familiar with it, is whenever you're working with thin materials, such as this one right here, there is something called a shell that we can use out there. And there's reasons why we will want to use shells and maybe reasons why we would not want to. I chose not to use shells for this one because of some of the things that Julio is going to show us within his simulations here. So whenever you're working with solids, like we are right now, we want to make sure that we have at least 2 mesh elements across the thickness of any material in order to get reliable results. If you have less than that or right on that, we're going to be maybe rendering some of those results to not as accurate of a value as it could be. So if we take a look here across this thickness, or close to thinnest part here, each one of these triangles represents a mesh element. So I have 1, 2, 3, 4 mesh elements going across this thickness right here. So we're in good shape. I can definitively say this is a pretty good mesh right here for what I need. and we can go ahead and run this and probably get some pretty good results out of it. All right, so let me just hide that mesh here because it gets a little messy to look at. And let's take a look at the results here. Again, I ran this ahead of time. This one took probably about 5 minutes to run. It was not bad at all whatsoever here. So with our thrust going at full throttle right here, let's take a look at our stress and see, did this thing fail? All right, so now we can see, looking at the results here, I see some deformation. That's kind of interesting. Okay, no big deal. I see some pretty colors. Those pretty colors correlate to this chart that we have over right here, and I can definitively say this thing did not fail based on material conditions. How can I say that? Well, if it did fail, we would see a value for the yield strength down here at the bottom of our chart with an arrow indicating at what color on the model did our failure occur. So I don't have yield here anywhere whatsoever, which means we didn't fail. We're in good shape based on that force and based on our current geometry at this point. So that looks pretty good right there. Nothing bad at the moment. And we do see, like I said, some deflection right here. Let's take a look at that. I have a displacement chart that we can see. And we can see it looks like the max displacement for this thing is about a little over 1/4 of an inch right there. So that's not bad. It's looking pretty good at this point right here. Again, nothing's breaking. So we could probably at this point go back and tell the design team, yep, you did a good job, life is good. But I'm going to take it one step farther. This is basically at what you can almost consider a steady state, instantaneous loading, which we all know is not realistic by any means whatsoever. So I'm going to treat this a little more real life situation-esque here. So what I did is I moved this study into a nonlinear study. We were working with a linear static study before, and now I went to a nonlinear study. And again, maybe if you're not familiar with this, you might ask yourself, well, why are you going to a nonlinear study when the material isn't breaking whatsoever or isn't deforming? And that's a great question, because honestly, a lot of times people move to nonlinear studies when your material goes past a linear portion in the stress strain curve. When you start having permanent deformations, maybe not full breakage, but permanent deformations, and you want to know what happens after that linear curve. That's what these things are for. But we can also use nonlinear studies for time-based loading, which is what I want to do here. I want to say over a course of time, we're going to go ahead and go up to full throttle and then maybe take it off again. So that's what we're doing here. You can see the study looks almost identical right here. Everything's set up the same, the mesh is the same, the fixtures, the forces, but the difference here is, let me edit this force. If we take a look here, when you work with a nonlinear study, you have an option to use variation with time. So for this study right here, I decided I want to load this over the course of 2 seconds, load and unload, I should say. So if I take a look at my curve right here, I'm going to hit this view button. And this is how the study is set up. I have a total time of 2 seconds. We can see that on the y-axis down here at the bottom, or the x-axis, I apologize. And on the y-axis, this is where we have the force. So I'm saying at time equals 0, there's no force on it whatsoever. I want it to linearly increase until I get the time equals 1 second. At time equals 1 second, then we're going to be at our full force, which was that 0.4 some pounds of force right there, just under half a pound. And then after 1 second, I want it to start tapering off to 0 once we hit 2 seconds. So we can get a better idea of what's actually happening with those stress values during the loading. I want to make sure there's nothing kind of interesting happening on at those points in time. So these studies do take a little bit longer to run. This one took about an hour to run with that 2 second time frame, but that's because I did quite a few time steps in between to break down and get some really good data out of it. So I could have done maybe something a little bit more simple, but we'll take a look at this right here and see. Oop, looks like it's not going to be able to create it for me at this point here. I do have to rerun at this point. So I must have shut off SolidWorks, unfortunately. So I do apologize for that. What I'll do is I'll rerun this and I'll post the results in our trade show booth for us to take a look at. I'll show you a link for it here. But basically, when we see those results, I'll show you an animation of it where it's going to show the loading and unloading across that 2 second time frame. But regardless of that little mishap right there, even with our regular linear results at this point, we have a really good design. So I can now go back to the design team and I can say, hey, from the thrust standpoint of almost a half a pound at 14,000 RPM with our blade designs we have a valid design at this point. So we're in good shape now. But before we specify all that information to them, we're going to turn it over to Julio now, who's going to basically drop this out of the sky and see what happens as it hits the ground. So there's some more details to this besides just an FEA. So I'm going to go ahead and pass it over to Julio here to finish off this portion here for us.
Awesome. Thank you very much, Ryan. You did a great job, but I'm about to drop it, man. All right. So yes, my name is Julio Calles. I'm one of the application engineers here at Design Point. And then now the next phase of the simulation presentation that you guys are watching is going to be pretty much the drop test analysis and the tools that we use for that. So as you noticed, Ryan, my colleague, he utilized flow simulation as well as SolidWorks simulation to conduct the FEA as well as the CFD portion of the design validation for the quadcopter. So let's take a look. So I'm going to be using the SimuliaWorks portfolio, and this is actually available right on the platform. Now, based on that, the platform, if as my colleagues would probably in some of the webinars that you have attended, there's actually what are called apps and then roles. So the role that I'm going to be utilizing to conduct this type of simulation is called the structural mechanical engineer role. And then we're going to be using also an app. It's pretty much one of the highest level of these type of simulations that you can do right on the platform. Now, one of the reasons why I wanted to use Simulia, it's mainly due to the collaboration capabilities, being able to get in touch with our colleagues very easily and pretty much have one single source which we can post all of our comments, designs, and so on. In addition, it also has the ability to utilize cloud computing. And by that, what I mean is that you have the ability to run your simulation off a server. And that actually can help you solve simulations a lot faster. Now, from my personal experience, what I would say is that you will really see the advantage of cloud computing whenever you perform some simulations that normally would take, probably over an hour. Anything that runs perhaps within a couple minutes, you won't be able to see much of the difference. Once again, given the entire workflow that the software has to go through to run this type of simulations of a cloud. So as far as the materials, I'm going to be consistent with the setup that Ryan showed you guys. So I will be using the frame and the shell for the battery, both made out of onyx. Now, I will not be incorporating the blades or the propellers as well as the motors in this case, given that we're purchasing those from a manufacturer. So we were not tasked to test them on this case. But if we had to, we certainly could. We could just add them to our analysis. We know, once again, from the manufacturer website that the propellers are made out of polycarbonate and the motors are made out of alloy steel mostly. So I'm going to walk you through some of the setup, okay, that I did for this type of analysis. Basically, I broke it down into two different setups. And one of the reasons why I chose also to go right away with Simulia to conduct the FEA test analysis, that you actually have the ability to run a drop test analysis in SolidWorks simulation, given that you have the correct package. Now, when you do a drop test analysis in SolidWorks simulation, you actually notice one thing, and it is that you're only able to see one bounce of your model. And by that, what I mean is that you're only going to be able to see the results, stresses of what happens to your model that very millisecond, or that couple seconds when your model hits the floor. In Simulia, due to its solvers that it actually utilizes, you actually have the ability to simulate multiple bounces. So for the initial setup that I did, I simulated indeed actually a couple bounces and be able to understand which ones of those gave me the highest levels of stresses. I'll also talk about the final setup and some of the difference, talking in regards to the time increments as well. So let's go ahead and just jump right into Simulia. Let's see what that is going to look like. Okay, so as you can see right now, this is what the platform in this case will look. We're using the Physics Results Explorer app in order to essentially browse the results of our simulation. It's very similar to SolidWorks. So you see on the left side of the screen, you have your design tree where you have your models, the setup that you did as well, and so on. Then I have different scenarios in here. So in this one right now that I'm showing you, I'm going to show you the final one. Now I will post the video, the very cool animation of the multiple bounces. Just given that we're running on a very small time frame, I just didn't have the time to show you both scenarios. So I wanted to show you in this case the worst case. So let's walk through some of the iterations that I did. So in the first analysis that I did, so that first test, I did a very mild simulation. So I just dropped the quadcopter from a height of roughly 16 inches. In the second one, I used it 50 feet, right? So we try to bring it up to 50 feet and see what happens. There was a couple learning lessons in this type of simulation. So for example, when I did this drop test, I began to utilize what is called an explicit solver, which is available in for Simulia. And one thing that you needed to make sure that you play around with, it was the time increment. Okay, so if your time increment is too large, you won't be able to see, right, certain scenarios, certain iterations of your simulation. In this case, I had to come back and take all of those learning criteria that I did in my first study and bring them into my final test. So in this case, I made my time increment very small. That way I'm able to record, right, that instance of time when the quadcopter hits the floor. So in some additional things that I did as far as the contacts that I have going on is that I have the battery shell and the frame. In this case, I have them bonded. And that type of contact definition, what I'm telling the software is that these two surfaces are almost like glued together. Okay. Now, this may not be the exact real life correlation on what is actually happening, but just for this study, it's accurate enough for us to obtain some results. Then I specified a couple other things. So I used some kinematics equations back from college just to try to understand what my initial velocity would be. So I am not going to essentially put in the simulation 50 feet apart from the ground because that would just take forever to run. So in addition, I also added this bottom plate here, and that bottom plate is to simulate the ground. I also specified it just to help us run the simulation a little bit faster. I did what is called a rigid body. And a rigid body is pretty much a body that will not deform in your simulation. So therefore, the software doesn't have to exhaust any resources from your computer to calculate the stresses, right, strains that could happen to that body. So that's one quick thing that I did to help us run this a little bit faster. Then as far as the restraints, I have what is called a clamp here in Simulia. It's very identical to what a fixture is in SolidWorks simulation. Okay, so in this case, I'm just apply a clamp to the bottom face of our plate. That way, as the quadcopter hits the plate, right, it doesn't translate down. And then I just have some general contact, just some friction, in this case being applied to it in between the bodies and so on. So let's go ahead and take a look at the results here. Everyone really loves, of course, a very good animation. Okay, so you can see here, in this case, what is actually happening. And this is one thing that I was unable to get the first analysis that I ran. The first analysis that I ran, some of the iterations, it was not recording the stresses that was happening the second that it hits the ground. But now, since I made my time increment very small, and I can actually change them here. So let me do a couple of ones here. So roughly around, let's switch to a different step. You can see here, I believe I was around 4. Here you go. So you can see here some of the good stresses showing right away. Okay. And actually one really cool thing that I learned is that one of the highest stresses, it actually happens as the quadcopter begins to lift up. So it doesn't happen when it hits the ground. That's actually something really cool that I learned. It happens as it begins to lift. And that's actually something that was called almost like a whiplash, right? So that creates a very high stress in this case, in this area of our model. So something that was very cool to see. One other thing here that you can also do in Simulia is that you have the ability to specify different steps. Okay, so to specify different steps is to help you reach some level of conversions for your simulation studies. So let's go back here to our PowerPoint. Let me just post it. Okay. So I'll tell you about some of the stresses that I obtained in the initial results. So I obtained roughly 1.23 e to the 7 pascals. And then in the final results, right, as I mentioned, we did a drop high of 50 feet. Our highest results in this case actually went up quite significant to 8.34 KSI, but this is actually still well below the yield strength of this part. And then we also, as I mentioned, we drastically reduced the time increments that we were utilizing for this type of scenario. So in conclusion, what did we achieve? So our drop test showed that our design is safe for this scenario. And that's the reason why I highlighted the word this. So in the simulation, okay, the setup that I did is from 50 feet. So we don't know what could happen if it goes for 60 feet, 70 feet, or so on, right? So we're only validating this particular instance. Now, there's another thing here that also comes into place. Well, what about the batteries, right? The batteries now bring some sort of chemicals, which could, as it collides with the ground, it could potentially explode. Okay, so that's also another criteria that could also be taken into place. And then as Ryan showed you, our FEA and our CFD analysis both verified that there was no failure in this design. So we can say that we have successfully validated our design for the quadcopter. Some of the next steps that we can do is that we can share the findings with our team, and we can stand by on any additional changes that they would like to do. Perhaps if it's safe enough, right, we can begin to remove some material, make the quadcopter lighter, and so on. And then based on those findings, we can go ahead and rerun this simulation. Alrighty, I hope you guys enjoyed it. Right now, I'm going to leave some time for some questions and answers. So stand by here. And by the way, if we run out of time with any of this, with some of the questions, please feel free to visit us at our Sim booth, and we'll be able to also answer your questions there.
Awesome. Thanks, Julio. Yeah, if you guys have any questions, please feel free to pop them in the chat. You can either put them in the chat, and there's a Q&A section there as well. So if you want to place those in there, we'd be happy to answer those. We'll stick around for a few minutes here. And like Julio said, we'll be hanging out in the simulation trade show booth here after this. If you have questions that pop up then, like I mentioned, I'll go ahead and post the results that I came up with for the nonlinear study in there if you guys want to take a look at that video when it's completed.
Excellent. And I'll be also posting my my animation of the first drop that we did. Stop sharing my screen here. Let's take a look.
Anybody in this presentation never use or see simulation before?
Oh, we actually have a question here. So I have a question. Did you account for the mass of the batteries and motors in your simulation? The unsprung weight of the motors would change your impact results. More force in your arms. For the drop test, in this case, no, we did not account for that in the drop case. As far as the batteries, we did make it the battery shell quite solid, and we try to compare the mass with what the mass would be with the batteries, and it was quite close.
Got another question here, Julio. It looks like it's for me actually here. It says, I mentioned that I was confident with the linear static results. They passed because the yield strength indicator did not show up on your stress plot. It looks like he says, I see the yield strength indicator regardless of pass or fail. Can you speak to that at all? Yes. So that is a setting that you can put into SOLIDWORKS to basically show the yield strength value all the time. Now there are some mass properties, or I'm sorry, not mass properties, material properties that have to be inputted to your material library to make that always show up. But there is also a setting where you can have that showing all the time. And then in the case of, say, a pass, the arrow and the value will only be at the bottom of the chart instead of throughout that chart value. So I just didn't have mine turned on for this one. Looks like there's one here for you, Julio. Can you account for air resistance during the drop? And what if it flips and lands on the edge? It's a great question.
Yeah, that's a really good question. No, we did not. So one of the assumptions that we didn't do any air resistance, which could essentially affect the design itself. And then what if it flips and lands on an edge? So in my first study, I did do multiple bounces. So it didn't, based on the multiple bounces, it didn't actually flip and land on the edge in that scenario. And by the way, one thing with Simulia is that this tool is pretty new to us. So I've been learning pretty much as I worked on the tool. So by no means I want to portray the picture that that I'm an expert. I'm probably a little bit more familiar with SolidWorks simulation than with the SimuliaWorks portfolio. But there's so much power that can bring in there, especially with the nonlinear analysis that you can do.
To kind of piggyback off that question, one more thing here, Julio. Again, to kind of show the power of Simulia, because the question might pop up, why would I want to get another tool to do a simulation when I already have something in SolidWorks? And it's, it comes down to, you have a nail you want to pound into a board. You can use a screwdriver if you want. But you might want to use a hammer in this instance. So, that was a great question, asking for multiple bounces. What if it flips on its edge? I remember Julio showing me the results of some of these things. Like he said, when he did a longer study, it did kind of teeter a little bit, but I guess because of the center of mass and everything, it did stay flat. But again, that's not something that we can do in SolidWorks Simulation Professional with the drop test. It's only that instantaneous hit. So we wouldn't be able to tell within SolidWorks if it bounces multiple times. So those are the important questions to ask. What is it that we're looking for out of the results of our simulation studies to help determine what is the best tool to go after for it?
And right, I have one here for you.
Ooh, all right.
It's in regards to the transfers between flow simulation and structural simulation. Did you do that?
Yes, we did do that. So now I did kind of a fake transfer, if you will. So what Rusty's referring to is, because I use two tools that are directly in simulation as an add-in, or I'm sorry, within SolidWorks as an add-in, you can take the results, the flow results from flow simulation, and directly pump them into SolidWorks simulation. So we can get those force values and so on and so forth. But because I decided to simplify the study for removing the motors and the propellers, it won't allow you to remove those things. So whatever you have in your flow simulation study physically has to be in your FEA study physically as well. And just because of time constraints, that's why I decided to go that route. So what I did is I took that force value and just basically read it off and then apply that to the model. Now, that might not be the best practice. And, I'll be completely honest with that, because if I were to ever go back and change something like the rotation speed, maybe the blade design, anything like that, my flow simulation will update. But because I decided to take that communication loop out, then I need to remember to manually go back to my FEA study and update whatever force value I pull out of flow simulation. But if I was willing to keep everything in there, it would have all stayed connected and gone perfectly just like that. So it just depends what direction you want to go. But that's a great point, great question right there.
Take a look. Any other questions?
Yeah, we still have a few minutes here if anybody has any additional questions.
I believe we're here until what, 1:45?
1:40.
1:40, okay.
So we got about 5 more minutes here roughly. Hopefully you guys learned something out of it, got something interesting, maybe considering trying out simulation, it's pretty awesome. Just in case you're not aware, if you've never worked with this before whatsoever, regardless of what type of license of SOLIDWORKS you have, you do have access to at least Simulation Express, which is it's a boiled down version of simulation, but it's still pretty powerful in what it can do. It's a good way to get your feet wet. It's under your evaluate tab. You can turn that on. If you've never turned it on before, it's going to ask you for a verification code. There's a link, you log into your customer portal account, and boom, it spits it out. Jump in there and you can run an analysis on a basic part essentially. But again, that's a lot of great information right there that you can utilize and try to play around with and see what you can do. And depending on other licenses you may have access to some of these other additional studies as well. So definitely play around with it. All right, guys. Well, I think if any other questions do come up, like we said before, we will be in the simulation booth here in the trade show portion. So be sure to go check that out. If you haven't, definitely get your points for your potential for winning some swags. So there's some pretty cool prizes there. Take a look at that. Oh, we got one more that's in here. Do you think the motor support structure was a good candidate for the topology optimization? Oh, absolutely. Yes, this would have been fantastic for it. So if you're not familiar with the topology that we're referring to here, that is a function of the actual simulation license, where what we can do is we can run the studies like we did as considered an initial state, and we can specify critical areas that have to stay as is or vice versa, and we can have the software actually remove material for us to meet some kind of a criteria. So you can do, say, a strength to weight ratio and specify that. So since we saw that our frame was good to go, instead of going back to the design engineers and saying, hey, go ahead and start pulling out material somewhere, give it back to us and let's see what happens, we can just run another topology study, as it's known as, to go ahead and do that for us. And then we can submit the new design to the engineers and say, hey, what you gave us the first time was perfect. It worked. There's some room for improvement. Here's the improved design if you want to implement it, and then go ahead and take a look at it that way. So that's a great method right there, taking advantage of the tools that you have. Especially for 3D printing too, because if you've ever used the topology study, it makes some really interesting geometry, which if you send that off to the machine shop floor, you might get something heavy thrown back at you. So you might need to do a simplified version of it. But if you're 3D printing it, you can make it almost identical to it, which is great. So. All right, everybody. Well, thank you very much for joining us right here. It was an absolute pleasure to show this stuff off to you. Hopefully you enjoyed it. Come check us out. Check out the other booths as well. Everything's great. We have a few more things happening here throughout the day, so definitely stick around and see what happens. Otherwise, hope you guys have a fantastic day.
Awesome. Have a good one, everyone.